Okay. So this differential equation for nu, again, non-negative integer, so nu could be like 0, 1, 2, 3, 4. Or you can also have nu as half integers if you're using this for spherical, and in general you can also solve this for any nu. But in our case, we'll only be interested in the case when nu is a non-negative integer. Okay? The solution of this equation is called the Bessel's equation. And this solution requires something more complicated than a power series solution. Okay? It requires something called Frobenius method. Now, we don't have time to cover Frobenius method. That's like another week of lecture. So let me try to make it brief here. So what we have here is you get this equation, first of all, from wave equation on a disk. And the difference between a wave equation on a disk and the Laplace equation on a disk is that you get something extra. Yeah. So if you recall, when we were solving Laplace equation on a disk, we had something like r squared capital R double prime plus r prime plus some, actually minus n squared r equals to 0. Remember this? We had this at some point, right? When we were solving Laplace equation on disk. Right? And I call that this is an Euler-Lagrange equation, no, Euler-Legendre equation. Is that right? Yeah, Euler-Legendre equation, or Legendre-Euler equation, right? Which is known to have the solution r equals to r to some kth power. And then if you plug this in, you end up finding out that k is either n or negative n. Okay, you remember that? So we had two solutions. We had r to the nth power, r to the negative n. Hey, we did this last week. Don't tell me you already forgot. Right, so we got this, and then, so the general solution is r equals to c1 times this and c2 times this other one. And we said this should be thrown away. Why?
It's not physical?
It's not physical because we're trying to solve the Laplace equation with this, where you get some voltage outside, right? And then you're trying to solve what's the electric potential shape inside this domain, right? So if you have some finite value and there's no charge inside, it's ridiculous to say that suddenly at 0 you have infinities or negative infinities. It doesn't make sense. So this should be thrown out. Oh, and by the way, there's something I forgot to say. You could also solve an equation where you know this end of boundary of a disk, but you're trying to solve the outside. You can solve that as well, right? In this case, it's this one that's non-physical, and this is the one that's physical, because this one, when you send r to infinity, it goes to infinity. That's not what you want, right? So being physical depends on which domain you're trying to solve in, okay? But just, if we limit ourselves inside the disk, then of course this is physical, this is non-physical, right? Okay. Now, if you think about this one by replacing r by y, and then small r by x and big R by y, it's basically this one except this one, right? If you get rid of this, it's exactly the same thing. But we have this extra if you're trying to solve the wave equation. That's what happens. All right. Now, what distinction does this carry? Well, it turns out that, see, one of them has a singularity and this other one doesn't have a singularity, right? It turns out that solution of the Bessel function also has that kind of a problem. One of them will have x to the negative nu type of singularity, and the other one will have x to the nu times some function, some power series here. Power series. And by Frobenius method calls this one as r, not that r, but let's say r is some constant. That's how people write down. And so they take the solution to look like y equals to x to some r. Here is a constant, not the variable. Don't think about that r. some constant r times an x to the n starting from 0 to infinity. So what's that? That's like the power series with possible singularity at 0, right? If r is negative, then it will have a singularity at 0, right? You see that? Okay. So having this as your ansatz to plug in, if you like have a predetermined form of a solution and you're plugging into the differential equation to find the solution, that's called an ansatz. It's a German. Does anyone speak German? Okay, so I guess I can confidently say what this means. It means like a sentence, right? So it's some sentence. You plug in some preformed solution, you plug it in, and then you figure out what these could be, right? So that way of solving it is called a Frobenius solution, and that's another really big topic, okay? But because we're trying to solve for a disk, right? We're going to throw away this type of solution, and therefore we're going to throw away this type of solution, and we're only going to have this one. And because we are only allowing our nu to be an integer, right? This, when you multiply it inside, see, if you have this and you multiply it inside, that's again sigma n equals to 0 to infinity of an to x to some integer power, right? If an integer power, this is still a power series, right? Okay. So that's why I titled this part as power series solution of the Bessel's equation. Is it okay? Does it make sense? All right. So for our purpose, it's okay to limit only for this one. But of course, if you want to solve the wave equation, it doesn't make sense to have a wave equation that's outside the circle. It's a bit strange. But let's say if it's possible, then you would have to treat the other ones as well. Okay? Okay. And the two solutions of this equation are called Bessel's function of the first kind and Bessel's function of the second kind. The second kind is the one that we don't like. It has a singularity of 0. So we're only looking for the Bessel function of the first kind. Okay. Now, after our next exam, we will talk more about the Bessel functions and its properties, some identities that it enjoys, and you will slowly try to gain insight into what this function does. Okay. But today, I will just solve this for, say, nu equals to 6, right? So let's just put 6 squared here, okay? Nu equals to 6. And the question would be, instead of finding the general solution, since we've already tortured ourselves to one example, it took more than an hour. We don't want to do that, so we'll just say, find first, let's just say 4 non-zero terms. Now already this is going to need a serious calculation, so please, if anyone has a calculator, please have them ready to assist me, because later on will be like crazy numbers out there. Okay, so if you have a calculator app on your or tablet or something, you can also use that. So please be ready to assist me. Okay, and then for general solution, you can look at some textbooks that have the general solution worked out. It's not that pleasant following it though. All right, so let's try to solve it. So what's our assumption? That y is a power series. And if you differentiate this, n comes down, and you have to subtract 1. And then the very first term disappeared because it's a constant term, so now n starts from 1 to infinity. Y double prime, n starts from 2 to infinity of n minus 1, an x to the n minus 2. Plug everything in here, but as I said, you really want to distribute terms if you have more than one term inside the coefficient. So here you have x squared y double prime plus xy prime plus x squared y minus 36y equals to 0. And we're going to plug everything in. So x squared summation n from 2 to infinity n minus 1 a n x to the n minus 2 plus x times summation n from 1 through infinity n a n x to the n minus 1 plus x squared times summation n from 0 through infinity a n x to the n, and then minus 36 summation n equals to 0 through infinity a n x to the n equal to 0. I hope I'm not too fast here. Yeah. Okay, and then we move things that are multiplied outside to inside. And I already explained that that's really distributive property, that this is gigantic summation, and then things that's multiplied outside can be multiplied to individual terms inside the summation. So that you get summation n equals to 2 to infinity n minus 1 a n x to the n plus summation n from 1 through infinity n a n x to the n. And notice how I just, when I brought inside the x squared times x to the n minus 2, the exponents add up, so I write down x to the n. Same thing happened here. This is x to the first power, 1 plus n minus 1 is just x to the n. And then some plus summation n equals to 0 through infinity a n x to the n plus 2 minus, plus summation n equals to 0 through infinity negative 36 a n x to the n equals to 0. Okay, so again we have 4 factories. One of them we would like to shift. Which one do we shift? Do we shift this one? This one? This one? This one, right? It's this one. Okay. How do we shift?
Minus 2.
Yeah, replace n by n minus 2. So we do n replaced by n minus 2. And the result is that since n minus 2 equals to 0, we write n equals to. If n minus 2 is equal to 0, this is the same as n equals to 2? 2. To infinity of a n minus 2 x to the n. So it's everything else is the same, but this one is replaced by this one. Okay. So we did the shifting, right? See, really, everything else is straightforward other than the shifting and splitting off of the terms. Okay. Okay, so now we should combine all these sigmas to a single thing. For that to happen, n should start where? At 2, right? So n equals to 0 and n equals to 1 terms should be split off from the summation. Okay. All right. So n equals to 0 term. What do we get from n equals to 0? That's what we get, right? They don't produce anything. This one doesn't produce. This one doesn't produce. This one doesn't produce. This one doesn't produce. But this one does. When n is equal to 0, you get negative 36 a0 x to the n. Right? Okay. And then plus. When n is 1, what does it produce? This one's silent. What does this one produce?
A1.
1 a1 x to the first power, right? So you get just a1 x to the first power, okay? And this one also produces something. What does it produce?
Negative 16 A1.
Negative 36 a1 x. Okay, those are the only terms that correspond to n equals to 1, right? Okay, then after 1, everything now can be put into single sigma starting from 2, which gives you, so let's do this. This one, and this one, they all have ANs in there. So I will be factoring out the x to the nth power out, but I also want to put these together with a and b factored out. So if you do that, here's what I get. I get n minus 1 plus n minus 36 of an. Is that okay? Yeah, I'm skipping steps compared to the previous question I solved. But all I did was I took these 3 terms and I factored them an out because all of them have an's in there. But this one doesn't have an an. It just has a n minus 2. Okay? And that has to equal to 0. Okay. So the second challenge, so you just have to know shifting and splitting off terms. And we're done with the 2 challenges. And now we just have to read what the result says. Okay. So what does this tell us? For that to equal to 0 as a function, what do we know?
AO equals 0?
Yeah,
Right.
this has to equal to 0. Yeah. And this has to equal to 0. And this one has to equal to 0. Okay. So that's what we get. Oh, there's another thing that I forgot to say. See, when x is 0, y double prime vanishes, and this one also vanishes, and you get something strange, right? So this equation has a singularity at x equals to 0. Another way people explain it is you write this as you divide x squared by everything, so that you get y double prime plus 1 over xy plus this thing over x squared y. Then these coefficients have x equal to 0 as a singularity because it's in the denominator. The functions are not defined at x equal to 0. Now, whenever that happens, you no longer have the uniqueness. So, for example, y of 0 and y prime of 0, even if you provide those 2 values, you can't guarantee the uniqueness. In fact, I mean, such solutions wouldn't, a lot of times they wouldn't even exist. Okay? Instead, what happens is that for this equation, if you provide the value at other values other than 0, say y at 1 and y prime at 1, if those values are provided, then there's uniqueness. There will be 2 free parameters. So such a thing still works in some way, but away from 0. 0 is a singularity. Okay? So it's a bit strange to see your equation working out so that the very first a0 is forced to be 0, because you thought that's a free parameter, but in this case it's not. A0 is forced to be 0 because we're looking for a solution that it doesn't blow up at 0. Okay? So that's the reason that you have such a strange result is because you have a solution which is singular at 0. Okay. So as I said, all of these coefficients must be 0. That's the property of power series. Then you get negative 36 a0 equals to 0, which will imply that a0 is 0. Now a1 minus 36 a1 is negative 35 a1, right? That also has to be 0, so we know that a1 has to be 0. Okay. This is n squared minus n plus n, so that's n squared minus 36 an plus an minus 2 equals to 0, and this is valid for n greater or equal to 2. Okay. Because the summation starts from 2. Okay. Now for this one, which one do we solve for? An, we solve for an, higher index, always, right? Okay. Yeah. So we say n squared minus 36 an is equal to negative an minus 2. We divide we get an equals to negative 1 over n squared minus 36, an minus 2, and that should be valid for 2 or greater. Now, from previous experience, it's also beneficial to factor this, okay? So we are going to factor this, n plus 6, n minus 6, an minus 2. Okay, and always in your solution, put a box around it because I want to see it. Okay. What is this thing called again?
Recurrence.
Recurrence relation, yeah. Or recursive relation. Okay, so what's A2? A2 is something times A0, right? Well, what's A0?
0.
0. Uh-oh. Does that mean anything, everything is 0?
Is it just the evens would be 0 then?
Oh, let's keep going. A3 is something times A1, right?
Yeah, it's also
So it's
0.
again 0. Okay. Now, when's the first time you can't say that it's 0?
All of A is 0.
No. Okay, A4 will be something times A2, because A2 is 0, it's going to be 0 again. Okay. A5 will be... Okay, what about A6?
It doesn't exist with infinity.
This thing breaks down at A6, right?
Yeah.
Why? When n is 6, you get 0 in the denominator. So if you go back and see what it says, if you plug in n equals to 6, it says 0 times A6 is 0. You get that?
Yeah.
0 times A6 is 0. So,
A6 is
so what, for n equals to 6, you really get 0 times A6 equals to A4. But what does that say?
so A is
That
6.
means A4, which is 0. So you get A4 is 0. So you need this. What satisfies this? Anything. So you can make A6 as non-zero. So that's going to be our first non-zero term. But wait, what does that mean? See, A6 is the coefficient of x to what power? X to the 6th power, right? So as I said, Bessel's function of order nu would be divisible by x to the nu power. This is 6 squared, so it'll be, I mean, you know that x to the 6th power will be the first non-zero one. Okay? And knowing this will kind of help you if such a question is on the exam, because you'll be puzzled. It's all giving you 0, so when am I going to get non-zero one? But now you know. Okay. So A6 is the first non-zero value. So A6 is A6. Now let's call this, say, some non-zero value. Some non-zero value, okay? Then, well, A7 will be 0, because A5 is 0. But then A8 would be what? Negative 1 over
N plus 6 and minus 6.
14 times 2. So 1 over 28 times A6, right? Which means now you can represent everything in terms of A6. A6 is our first non-zero one, so just represent everything in terms of A6. So A10 would be negative 1 over 10 plus 6 was 16 times 4, right, which is 64. A6, oh no, A8, but then that means it's 1 over 64 times 28, A8. Okay, somebody with a calculator help me. 64 times 28 is?
It's A6, right?
Huh? Oh, A6, thank you, A6. But 64 times 28?
1,792.
1,792. A6, all right. Okay, so how many non-zero terms have we found?
3.
3. A6, A8, A10. So we need to go
A12.
just A12 and then we're done, right? Okay, so we're going to go for A12. A12 would be negative 1 over 12 plus 6 is 18. 12 minus 6 is 6. So that's 72, right? 72. No, 108. 108. A10. Okay. So now you have to do minus 1 over 108 times 1,792. A6. What's this? Huh?
It's 193,536.
193,532.
93,536.
36?
36.
Okay, 36. All right. So we got our 4 non-zero terms. And here's another important thing. You don't want to finish here. You actually want to write this as a summation notation. You have to write down your answer as summation. So you write y as a0 is 0, a1x is the next one, but that's 0 too. A2x squared, that's 0 as well. So the first thing that's non-zero is what? A6 x to the 6th power. Okay. And then A8 is minus 1 over 28, A6 x to what power? 8th power, right? And then the next one is plus 1 over 1792, A6 x to the 10th power, right? And then minus 1 over 193536, A6 x to the 12th power. And the important thing is, after this, what should you write?
And it has to be greater than 2.
Plus, no, n greater or equal to 2 is for the recurrence relation. This is your answer, because that's different. Plus, dot dot. You want to write that so that it's an infinite series, okay? So it just keeps going forever, right? Okay, so that will be your answer. But let me say a few other things about this. So, how many free variables does this one have?
1.
Just one. It's a second order differential equation. You just found the solution with one free variable. What does that mean?
There's one more.
Huh? There's one more, exactly. There's another solution, okay? And the other one is that the one with singularity that I talked about. For that one, you have to use Frobenius method to get it, okay? And because we didn't learn Frobenius method, we'll just be content with getting just one of them. But this is the physical one anyway, so we will be happy with this one.
Why is one more?
Second order differential equation should have 2 free parameters. I only have 1. Right? Another thing that you want to do is you really want to factor a6x to the 6th out so that it looks like a6 x to the 6th times 1 minus 1 over 28 x squared plus 1 over 1792 x to the 4th minus 1 over 193596 x to the 6th.
36.
36? Yeah. So if you write like this, then first it tells you that there's only one free parameter, right? So every solution of this with no singularity at 0 will be just some multiple of this function, okay? So this function right here, with some chosen a6, is going to be called the Bessel function of the first kind, okay? And if you just look at this part, then you can just take this much, and then you can graph it using different values of x, and you'll get some graphs, okay? And there's some physical interpretation of what's happening with that graph, so we can talk more about that next time.